Welcome everyone to day 10 of Advent of Code 2023. The puzzle just opened a moment ago, so we're going to jump right in. Pipe maze. Uh-oh. Mazes. You use the hang glider to ride the hot air from the desert island all the way up to the floating metal island. This island is surprisingly cold, and there definitely aren't any thermals to glide on, so you leave your hang glider behind. You wander around for a while, but you don't find any people or animals. However, you do occasionally find signposts labeled hot springs, pointing in a seemingly consistent direction. Maybe you can find somewhere at the hot springs and ask, maybe you can find someone at the hot springs and ask them where the desert machine parts are made. The landscape here is alien. Even the flowers and trees are made of metal. As you stop to admire some metal grass, you notice something metallic, scurry away in your peripheral vision, and jump into a big pipe. It didn't look like any animal you've ever seen. If you want a better look, you need to get ahead of it. Scanning the area, you discover that the entire field you are standing on is densely packed with pipes. It was hard to tell at first because you're the same metallic silver color as the ground. You make a quick sketch of all of the surface pipes you can see, your puzzle input. The pipes are arranged in a two-dimensional grid of tiles. So we have vertical pipe, horizontal pipe, a 90-degree bend connecting north to east, 90-degree bend connecting north to west, south to east, south to west, south to east, ground. There's no pipe. Okay, so no pipe there. In your starting position, or in the starting position of the animal, there is a pipe on this tile, but your sketch doesn't show what shape that pipe has. Based on the acoustics of the animal's scurrying, you're confident the pipe that contains the animal is one large continuous loop. For example, here is a square loop of pipe. Okay. If the animal had entered this pipe in the northwest corner, the sketch would instead look like this. In the above diagram, the S tile is still a 90-degree F bend. You can tell because of how the adjacent pipes connect to it. Unfortunately, there are also many pipes that aren't connected to the loop. This sketch shows the same loop as above. In the above diagram, you can still figure out which pipes form the main loop. They're the connected ones to S pipes. Reading is hard. They are the ones connected to S pipes. Those connect to pipes. Those pipes connect to, and so on. Every pipe in the main loop connects to its two neighbors, including S, which will have exactly two pipes connecting to it, and which is assumed to connect back to those two pipes. Here's a sketch that contains a slightly more complex main loop. Let's see. Here's the same example with the extra non-main loop pipe tiles as shown. Where's the S? The S is there. If you want to get out ahead of the animal, you should find the tile in the loop that is farthest from the starting position. Because the animal is in the pipe, it doesn't make sense to measure this by direct distance. Instead, you need to find the tile that would take the longest number of steps along the loop to reach from the starting point, regardless of which way around the loop the animal went. In the first example with the square loop, you can count the distance each tile in the loop is from the starting. Okay, that makes sense. In this example, the farthest point is 4 steps away, yada yada. And then, yeah. Find the single giant loop starting at S. How many steps along the loop does it take to get from the starting position to the point farthest from the starting position? This is going to be a hard one. I can see it now. This one's going to be hard. We have hit graph algorithms. Okay. All right, so I'm thinking we want to build a graph out of this stuff where every node in the grid has its XY coordinates and it knows what it's connected to. And then we have to use that graph to do some sort of flood filling, Dijkstra, something. North and west, south and west, south and east, north and east. All right. Have you read the problem yet, Harrison? Read the problem. We've hit graph algorithms. Oh boy. All right. Let's see. So we're going to make a pipe object. Let's see. The thing is that some of these aren't going to be compatible with each other. And we have to ignore that lack of compatibility. All right, self dots. Self dot neighbors. Self dot connect the neighbors. I feel like that's going to be useful to differentiate what's a neighbor that's connected and not connected. All right. So we have our thing. So probably going to want to do a for I line and enumerate text for J character. Have you seen the puzzle input? Yeah, it's freaking massive. I don't know if we're gonna have time for Age of Empires tonight. Discord's. All right. I'm not great at graph algorithms. That's going to be my issue. Let's see. Let's see. Pipe. Going to be character and I, comma J. Just return for string. Return self dot. Let's see, pipe of shape. Self dot shape at coordinates. Just getting some stuff set up that should hopefully help me. I don't remember how to do F strings. I think it's like this. There we go. Okay. So determine the directions. So I'm not going to be the greatest at doing this in like a very quick and dirty fashion. So we're gonna flesh out, you know, a lot of useful objects. And or we're gonna flesh out this object, this class. And hope that it will help us, you know, work through things without getting, because I feel like if I try to just work with the stuff all willy-nilly, I'm gonna get confused and debugging is going to be a pain. So we're taking it a nice slow approach. So determine the direction. So if self.shape equals I think this character, self dot directions dot extend. Why is this getting bent out of shape about self? Oh, because I don't have parentheses here. North and south. Elif self.shape will equal believe that character dot extend east west elif self dot shape equals an L self dot directions dot extend north and east elif self dot shape equals a J northwest. This reminds me of a problem from last year that gave me a lot of trouble. 7 is south and west. F's in the chat. Southeast. Do these have to be like as a list? But we just do this. Oh boy, this is gonna be a lot of editing. Damn it. My ability of selecting multiple cursors at a time has like stopped working for some reason. And I don't know why. Okay. Return. Set. Did you set like that? Guess a set would be better, probably. Because the order doesn't matter and we're just checking to see if things are in things. Okay. Thank you. All right. It's braces. Damn it. Come on, fingers. This would be so much easier if I knew like Vim or something. Okay. So print x dot directions. So southeast. Yeah. Okay. That seems to be good. Now we need to do what? Probably would be a good idea to put all these in a grid. So we could do what? Grid of pipes equals empty list for X in do text, I think. One, two, three, four, five. 1, 2, 3, 4, 5. And then we could just append. Okay, so could probably do the following. I think we could do grid of pipes at I dot append X. So this would be at 1, 1. Print grid of pipes sweet. Okay. Now we need to connect them. Probably aren't going to end up using this. So pipes connect in the main cardinal directions, northeast, southwest. So how do we want to do this? Or do we want to connect them? I feel like the answer is yes. How to connect them. Think. So we look at a coordinate, and then we look at its neighbors, and then check if they have matching cardinal directions, like their shapes are compatible based off the cardinal directions. So like, and we only have to check the two. We only have to check the two directions that are with the shape. So for I line and enumerate grid of pipes. For J pipe and enumerate line. Let's just print the pipe. See what, so that works and everything. And then we can do print dot directions, and we get that. What happens if I would have returned an empty brace? Well, no, that would have been a dictionary, right? Okay. So let's see. For direction in pipe dot directions, can I iterate over a set? Yes. pipe dot directions. If direct equals north, do some stuff. Elif direct equals south, do some stuff. Elif direct equals east, do some stuff else. All right. So if we're looking at the north, then we want to be looking at what? The neighbor X, neighbor Y. Let's just do NX and Y. Equals X minus 1 and just Y. Because we're going up. If let's see. So if NX is greater than 0. Because if it's not, then we've gone off the page. Then look at neighbor equals grid of pipes at NX and Y. If neighbor dot directions, or I should say if south is in neighbor dot direction, then we do what? We do I think putting objects in a set didn't pose an issue, right? No, maybe. No, that I think that would be fine for what we're doing. Probably not a great coding practice, but it should be fine for what we're doing. The problem I'm thinking about is that I'm going through and I'm building this connectivity thing, and well, maybe so I'm worried about duplications, but if we only change the current node, then it should be fine. Yeah. So current pipe dots connected neighbors. Wish my auto completion would work. Dot append neighbor. Kind of a mess, but it gets the point across, I think. Can I check this out? Maybe I should call this build connections. Build connections pipe. So this guy is at 0, 1, 2, 1. Okay. Dots connected papers. What happens if I put an STR around that? Nope. Shape. Shape parentheses. Aha! There we go. Okay, I think that is working. Yeah, this seems to be working so far. Cool. All right. We are cooking with oil. So now we're looking south. So we want to look at x plus 1. So nx and y equals x plus 1 y. If nx is less than the len of the grid, then neighbor equals nx and y. If so we're looking below, so we want to check to see if this connected. Okay, cool. Huzzah! Cool, cool. All right, so we're going to the east. So x stays the same, y increases by 1 if this is less than the length of the a line. And then we want this to be west. And if this is greater than, I want this to be greater than or equal to 0. Yeah, greater than or equal to 0. East. This should be y minus 1. I'm mixing my x's and my y's, but I'm mixing them correctly. These are y's. Whatever. For item in grid of pipes. No, let's do it this way. Print pipe. And then for neighbor in pipe dot connected neighbors, print in print okay, so F has a neighbor there and there. Dash has a neighbor of that, and that. Okay, cool. I think we have everything fleshed out. The problem is the S. We have to figure out what the S should be. So S will have exactly 2 neighbors. And 2 connected pipes. So if pipe dot shape is not equal to S, so I have to do that one separately. Now the F here. Yeah, so the dash doesn't see that yet. So handle neighbors of S. How do we want to do this? I think we'll just handle that kind of separately. So I think we want to look at S's neighbors. So if S if Sx minus 1 greater than equal to 0 and south Start dot append. No, start dot connected. Neighbors. Append. This is messy. I don't enjoy this. Sure. So we look below. Cool. Now we need to look left and right. Let's see. SY -1 greater equal to 0. If we're looking left, then we want the neighbors to be an east neighbor. Plus less than len grid 0 west plus write them in start dot connect the neighbors print item. Perfect. So S has those neighbors, and then those neighbors, and then that. Okay. What do we do? We need to, so I think we have everything we need to actually like do the algorithm, and probably a lot more than what we need. We need to start at S, and we need to go outward in both directions. Until we hit the same node, basically. Is there... It sounds like from the problem statement that the furthest node is going to be unique. 1, 2, 3, 4, 5, 6, 7, 8. And I think that just comes from if there's an even number. There's 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, 2 6s, 2 7s, 2 8s. So really what we're looking at is if we go outward, so if we go outward this is like our start, and we go outward and just keep going away from start, we're going to get to a point where the next step from both nodes will go to the same. I think that will be the gist of it. How do we kind of work through this? So we look at our starting node. We look at our two directions. So we could do like some sort of like mark visited sort of thing, so that we don't walk backwards. So we start at S and we say the current nodes are going to be the neighbors of S that aren't visited. So let's add a visited attribute. And let's add a distance attribute. That may be useful. So we start at start. I've named above. And we could do while true or something, I don't know. The current nodes equals start dot did. So while current nodes node equals current nodes dot pop. If for item in node dot visited for neighbor in node dot connect neighbors. If in dot visited equals false, we want to, so we do this, we look at its neighbors. If it's false, then we want to look at, I think what we want to do is we want to do current nodes dot append in, and then I think we want in dot distance to be equal to current node dot distance plus 1. And then I think we want visited to be set to true. If pipe dot distance greater than 0. That's not right. That is way wrong. Where did my console go? That's correct. That's correct. That is not correct. What the hell? Get out of here. I'm reading. Oh, it's not. I see. It's not doing like a flood fill like thing. It's doing depth first. Or no, it's doing breadth first. I can't do one node at a time. I need to do both nodes simultaneously. Current nodes will start dot connect the neighbors. We look at. Actually, we might be able to do it this way, maybe. I think we might be able to get away with doing it this way. No, still not right. All right, let's see. So we have those two nodes. And we want to look at, we want to look outward, both directions. How about we do this? For item and current nodes. That's not. Well, no. If I do it this way, pop one out, Do the thing. Append that in. Why isn't this working? Also, what's the other way of doing string stuff? Is it... I think it's RER. Yeah, that's what it is. Okay. So we have these two. And then we have these two. Maybe I need to do pop 0. That's probably it. I'm supposed to do pop 0. I'm still not quite right though. Getting closer. I think that's what it was. Yeah, that was what I was. My intention was to remove elements from the beginning of the list, not from the end. And it's pop 0. Okay. I think we're getting there. I think we might be close. Yeah. Max node equals none. Max distance equals 0. If pipe dot distance is greater than max distance, then max node equals pipe and max distance equals pipe dot distance. Excuse me? That's not what I want. Oh no, I want max. Okay, cool. All right. Let's try it on this behemoth. Cross your fingers. Please, 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 please. Yes. We did it. Part 1's done. What the hell is that? Oh no. Oh man, you quickly reach the farthest point of the loop, but the animal never emerges. Maybe its nest is within the area enclosed. Oh no. Enclosed by the loop. To determine whether it's even worth taking the time to search for such a nest, you should calculate how many tiles are connected within the loop. For example, you've got this. The above loop enclosed merely 4 tiles, the 2 pairs of dots. Okay. In the southwest and southeast, marked I. Below, the middle dot tiles marked 0 are not in the loop. Here is the same loop again with those regions marked. In fact, there doesn't even need to be a full tile path to the outside for the tiles to count as outside the loop. Squeezing between pipes is also allowed here. I is still within the loop and 0 is still outside the loop. In both the above examples, 4 tiles are enclosed by the loop. Here's a larger example. Okay. What is the loop? Is it? Okay, it's this thing. There's many random bits on the ground, some of which are in the loop and some which are outside it. In this larger example, 8 tiles are enclosed by the loop. Any tile that isn't part of the main loop can count as being enclosed by the loop. Here's another example with many bits of junk pipe lying around that aren't connected in the main loop at all. Here are just the tiles that are enclosed by the loop marked with I. How many tiles are enclosed by the loop? Oh boy. First we need to figure out what is considered in the loop. Like what pipes make up the loop itself. They're outside the loop. How do you say that it's outside the loop? Outside versus inside of the loop. How do we determine if a node is outside versus inside? Let's get some. This is tricky. Because the thing that's throwing me off, that all of these zeros or O's, they're completely surrounded by the loop, but they're not inside the loop. And I understand why, but I don't know how to tell the computer how to understand why. So the first thing I'm thinking about is flood filling. Like I want to put all of these things into connected component. So I'm looking at this and I'm seeing that you know, this column here makes a connected component, this dot makes a connected component, this dot makes one, this blob of O's makes one, this is one node of a connected component, these three eyes, and these two eyes. So just separate all these into connected components. That, I think that would be like the first challenge, is if I can group all of these together. Then the next challenge is, given a component, is it inside or outside of the loop? So if I start at a node, just scan outward, up, down, left, right, and any node that isn't visited, that isn't a pipe, mark it as visited, add it to this connected component, and mark it as visited, add it to connected component, and then move on. So we scan outward. Add things to a queue to do the flood fill like thing. And while that thing is empty, or while non-empty, then we just keep flood filling. Okay. All right, I have some ideas. I have some ideas. We're gonna implement some things. The first part is actually telling the class, the stuff, what is a part of the loop itself. So self.inLoop ? Part 2 seems tricky, yeah. Part one was easy once I had all of my tools together. But getting all of my tools together took 100+ lines of code. Okay, so checking if something is in the loop. What we could do, we could just do this. Saw before I can read it. Yeah, I fleshed out a lot of class function stuff. Because I didn't want, I wanted to have all the debugging tools ready to go, and I didn't use any of them. I took a very slow and steady approach, and I had one bug that I quickly caught and fixed on the test case. And my one bug was that I was popping from the end rather than the beginning of my queue. I was treating my queue as a stack. Okay. I always forget, for some reason, I always think that pop should be the first element, but it's not. It's the last element. Like I keep forgetting that I need to do pop 0 for queue behavior rather than stack behavior. But pop append without arguments on a Python list mimics a stack. And I want it to mimic a queue. That's my issue. Okay. I think I could build my pipe here, maybe? Or no, here. Down here. When I'm doing this stuff. No. Here. There we go. Because I could do this. I could the clearly start is in the loop. Start dot in loop equals true. Item dot in loop equals true. Node dot in loop. True. So these should all say true. Yeah. So, yeah. Cool. How do I want to do this connected component stuff? So we want to do a blood fill like thing. If pipe dot component visited equals false, components dot append pipe if here is less than or equal to I less than len primitive pipes and 0 is less than or equal to j less than len grid pipes at 0 turn true false return false. Okay. So while component no. How do I want to do this? We want to add them all into the component, but I want a queue. Search pop 0. We want to do what? We want to look north, south, east, west. If that component equals false and pipe dot loop false. Node if ij equals node dot coordinates. If what? Inbounds I minus 1j and just do it this way. Neighbor equals grid of pipes at I minus 1j if in dot basically gonna be this, right? If it's not visited and it's in the loop or not in the loop, like not a part of the loop, then we need to add it to the component and add it to the things of nodes that we need to like flood fill from. And then we need to do this for all of these, all the cardinal directions. So we have an infinite loop. Let's see it. Where's it at? Damn it. Oh my goodness. If component is non-empty, connected components dot append component. Okay. 001001. Correct. 0414. Correct. 22. Correct. 424344. Correct. Okay, cool. That seems to be working so far. I want one of the more complicated ones. I don't understand why all of the ones on the perimeter aren't also marked O. The bub loop encloses merely 4 tiles. The 2 pairs south, the middle dots are not in the loop. So is all the rest of them. So I'm not sure why they didn't include those. But let's I don't know if those dots are going to throw off my code. Or not the lack of dots, I mean. So this is the perimeter. This is that. This is that. Okay, cool. I have all my... so the flood filling works. We're almost there, actually. Like, we're really, really damn close. Because now that we have all of these things, we have all the connected components, we just have to figure out whether or not they're inside or outside of the loop. Like, we are one step away from finishing this, I think. So yes, I was only one step away from solving part 2, but unfortunately I had to finish this problem off stream the next morning. So continue watching the video if you would like to see my overview of how I ended up solving this problem. Hello everyone. We weren't able to finish day 10 part 2 in one sitting along with day 1. So I'm going to go over how I ended up solving day 10 part 2 after I got to sleep on the problem. And I'm going to stitch this in with the part 1 and discussion from part 2 from the first sitting of this. So not sure how I'm going to do all that, but I'll figure it out. So anyways, to part 2. So how did I solve part 2? Well, let's actually just remind ourselves what part 2 was. So part 2 was that we had our loop. So remember, we're talking about a loop of metal tubes or pipes, and we're trying to determine how many entries are inside of the loop. So you can think of the loop as like a polygon or a Jordan curve or something like that, and we're trying to count the number of points that are inside of this loop. And so here we have this, cluster of O's that are technically outside of the loop, even though it is completely surrounded by parts of the loop. It is considered outside of the loop, but these 2 pairs of I's, these are inside of the loop. So the way that we started working on this, and this is what we were able to do in the first sitting of this, was that we ended up breaking down all of the sort of connected components is the way I'm thinking about it. So we have, in this example, 3 connected components. These 8 O's here, this pair of I's, and this pair of I's. Those are all 3 connected components, and we stored each of the connected components. We stored all the elements that are in that list so that we could then classify these connected components. Because once we know that if part of that component is inside or outside of the loop, then the entire component is inside or outside the loop, and then we just take the length of how many things are inside of that component. So how did we do this? So this is a bit of a mess, but essentially what we did is we sort of did a flood fill where we started through, so we started a new component, and we're looking at what elements we want to sort of search outward from. And so if the item that we're looking at right now has not been visited, it's not a part of some other component, and it's not a part of the actual pipe loop, then we're going to add that element to the component, and then we're going to add that element to the sort of queue of things that we need to flood fill away from. And then we're going to say that it's been visited in the sense of it's been added to some connected component already. And so then while our queue is not empty, then we're going to pop off a node or a cell from our queue, and then we're going to flood fill outward. And so we do this north, south, east, and west. I know that there's a much neater way of combining these 4 cardinal direction flood filling into smaller amounts of code, but I don't know what that way is at this moment. So basically we have the same 4 things, just handling the different directions: north, south, east, and west. And so what we do is we look at the north, the south, the east, and the west neighbors of that particular cell that we're looking at, and check, is it been visited and is it in the loop or not. If that's neither of those are so both of those are false, then we know that that is a part of the connected component that we're currently working on. And we do this for all of the 4 directions, and then we just continue to flood fill outward, adding things that haven't been seen before. We know that all of these are going to be inside of the connected component that we're working on, and ignoring the pieces of the loop. And then if we have a component that is non-zero in length, then we add it to this list of connected components. So then, now that we have all of the components sorted out into their different connected components, we classify them. Are they inside or in outside? And this was the part that gave me a lot of trouble because I was having a hard time sort of understanding this like discretized version of this problem. Because really what you're thinking about is, or at least the way I think about it, is points inside of a polygon. And the polygon is in this discrete representation, and these points are, discrete points in the plane. And I was having trouble thinking about how to count the number of boundary crossings that occur. Because we know that if you are, let's say you are inside of the polygon, then you can, every time you cross the boundary, you're either, so let me start over. So if you're looking at a point and you have a polygon, every time you cross the boundary of that polygon, if you're looking at, kind of scanning outward in one direction, every crossing denotes either entering or exiting the polygon. And so if I can count that I cross the boundary an odd number of times before I leave the grid, then that means that I was inside of the polygon because I've left and came back. And then, ended up leaving. And so those odd crossings, denotes that you were in the polygon, you were inside of the loop. And I was having a lot of trouble figuring out how to count those things properly with the format that we were given. So first, what I ended up doing, and I don't think that it was necessary, but it didn't hurt anything, was I looked at all the connected components and ask the question, are they on the border of this grid or not? So let's look at this more complicated example. We have, a bunch of components along the perimeter of this grid. And we know that those are immediately just going to be outside of the loop. So that kind of helped me, throw some things out of the search space. Helped kind of clean things up out of my head, at least. So we sort of sorted these connected components into the ones that were on the edge, the ones that were on the interior, and then we just focused on these interior ones. So the ones that were completely contained by some of the metal piping, but not necessarily in the loop or not. So what we ended up doing to sort of solve this points and polygon problem was we figured out how to count the number of crossings. And that took a little bit of thinking, but we finally ended up getting it, which made me really happy this morning. So the points and polygon problem, maybe it would help if I just kind of brought this up. So let's see, how do I want to expand this? So here we can look at, how many intersections there are denotes whether or not you're inside or outside of the polygon. So, and you only have to worry about a single ray. So you start at your point and scan outward in the direction of some ray. And Zaya, thank you very much for the follow. So you scan outward, and the number of crossings denotes, whether or not you're in or outside of the polygon. So it's a matter of how do we do this scan? So the way that I ended up doing it is I picked I just took my connected component. So I'm looking at interior connected components, and I just grabbed the first element outside of it, got the coordinates, the IJ components of where it lived in the grid, and then I said, okay, just take the string, or take the list of remaining things in that row. So I'm on some row, and I just take the remaining elements of that row. Then I'm going to build a string. So this string is going to be all of the characters, inside of my grid after some point. So let's look at this O here. So I'm going to look at this entire row that follows that O. That is the, string. That is my array that I'm thinking about in this problem. So then for testing purposes, there were O's and I's and stuff in the examples. So I just left these in here. But these are the elements that we're going to ignore, or the characters we're going to ignore. They don't represent anything in terms of a crossing of our polygon. So we're just going to skip these. And so we're looking at all of the characters that we're not ignoring and things that are inside of the loop. And so there's a little bit of logical overkill. I'm kind of redundantly checking things, but that's fine. We're not worried about that. And so we are basically trying to build all of the characters that make up part of the loop and put them in this string. And then we noticed that a couple of pairs of characters, if you have an F and a 7, so that's denoting sort of a south to east, and then a east to south, so sort of like an upside down V. That doesn't really represent a crossing of our boundary. So those V's and upside down V's, which is what these two things are, those don't mean anything in terms of crossings. So when we have those paired together, they're not contributing anything towards our count. So I take my string and I just replace any pair of these letters to, replace them with the empty string, remove them completely from my string. Then an L and a 7 paired together, those represent just, sort of a diagonal part of the pipe, and the F and the J represents sort of the complementary diagonal shape. And so those are going to represent boundaries that we're crossing when we're doing this horizontal scan. And so then we replace these with vertical pipes. And so once we do this, we essentially take our string and replace it with vertical pipes exactly equal to the number of crossings that occur in that horizontal row. So let's see, if I put a print line string here, and we have the big data set, but we see that all of these are just vertical pipes, and the number of vertical pipes are the number of boundary crossings that occur for our polygon when scanning outward in this horizontal fashion. And so we know that if there is an odd number of vertical pipes, or odd number of crossings, then we know that we are looking at a point that was inside of the loop. And so then we just count up the length of all of these things, and that gives us our final answer. So we had most of the problem solved. It was just coming down to figuring out, how do we handle this scan? How do we understand what these combinations of characters are really telling us in terms of the shape of the pipe and whether or not we're crossing or not crossing the pipe. And it took, some drawing out of, some of these examples and actually seeing it happen on paper for me to finally make that connection. But once we got it, we coded it up and we were good to go. So that's going to be it for this explanation on how I ended up solving day 10 part 2. Again, I'm not sure how I'm going to stitch all the YouTube stuff together. I'll probably just try and make a separate video for part 1 and a separate video for part 2 like I did for day 5. It's going to be a mess. I'm sorry. It's just kind of the outcome of having to do these problems into multiple settings. But if you stuck around to the end, I really appreciate you hanging out and watching the video. And that's going to be it for Advent to Code Day 10 2023. Thank you so much.